Okay, next. We're almost ready to start designing digital systems. We've almost got all the tools. In fact, today and next time we're going to take like a detour to design some digital systems like with the like basic tools that we have already. So let's just go jump in. And let's start by just working out an example. So I'm going to say find the min-term expansion of this function. F is a function of A, B, C, and D, and is equal to A naught, B naught, or A naught and D, or A, C, and D naught. So find the min-term expansion of that. Right off the bat, there's a problem. What's the problem? We're missing some stuff, right? Or the min-term expansion. So for this particular function, how many variables is in this function? 4. Good. You gotta say it loud, say it proud. There's 4 variables, which means how many total min-terms? 16. Very good. Now each term is going to have how many literals?
4.
It's a trick question, right? It's the same as the number of variables. 4, right? Now these terms, do they all have 4 variables? No. They all have 2. Well, that has 2 have 2, and that one has 3. Right? So we're missing some variables, right? We've got some like blank spots in the expression that we need to fill in. So the way we do that is by taking advantage of 2 of our original theorems or properties of Boolean algebra. So I'm going to say this. I'm going to say add the missing terms by applying these 2 laws. The one that says x or x prime is equal to 1. And the one that says x and 1 is equal to x, right? We can use these 2 properties to essentially like add in the terms that are missing. And that looks like this. For the first term, that starts with a prime and b prime, what are the missing variables? C and D, right? So we're going to AND this term with C or C prime and D or D prime. Does that make sense? If you understand that part, everything else is easy, right? Whatever variables are missing from the term, we AND them back in by ANDing with that or its inverse, right? Because that's equal to 1, and ANDing with 1 is itself, so we're not changing the truth table by doing this action. So, or A prime or D, what are we missing? Yeah, it's B and C, so and B or B prime and C or C prime. Finally, A or C or D prime is missing B, so we're going to put in B or B prime. Now this next part sucks, right? Because what do we have to do? Distribute all of that message. I'm actually going to bring it over here. And say, yeah, there's no good way to do it. You just got to do it. You got to distribute everything through. If you get, after a little bit of practice, you can get kind of good at it, and you can know that it's going to be this and like all of the combinations of these things. And what I mean by that is, we know it's going to be, so A and B, or A prime and B prime is what we start with. And we're ORing with C and D, so it's going to be C prime and D prime, or A prime and B prime, C prime D, or A prime, B prime, C, D prime, or A prime, B prime, C, D, right? So I determined I had, and I covered all the combinations of C and D. It doesn't make any sense, you can still just distribute the old-fashioned way. All right, so the next one, A prime D, and then B and C. That's going to get us, this one's a little trickier. Let's just look at the notes there in front of me. So, A prime, B prime, C prime, D, or A prime, B prime, C, D, or A prime, B, C prime, D, or A prime, B, C, D. And then finally the last one, A, C, D prime is going to give us A, B prime, C, D prime, or A, B, C, D prime. All right, like I said, that was long, that sucked, but there's really no way to get around it. So the next thing that you can do is see if, well, the textbook is going to tell you the next thing that you need to do is look for the duplicates and eliminate them. But I think it's easier if you don't do that until after this next step. First question, do we want to simplify this? No, we don't want to simplify it actually, right? Because our goal is to find that midterm expansion. And now we've sort of drawn out all of the possible midterms. Basically, what we did in effect was we started with a simplified expression. And we said, like, well, if we took this back out, if we unsimplified it, what would we get? We would get this expression. So now we need to identify which minterms go in the expression. And the way we do that is the way we started with them, which is where we just kind of number them or label them by denoting that if it's inverted, that's a 0, and if it's non-inverted, that's a 1. Right? So A prime, B prime, C prime, and D prime is going to get us 0, 0, 0, 0, right? And in fact, let's go ahead and just start our generalized midterm expression down here by saying that f is a function of A, B, C, and D is equal to the sum of midterms, and we know we've got 0. The next one, A prime, B prime, C prime, and D is going to be 0, 0, 0, 1. That's midterm 1. The next one, A prime, B prime, C, D prime is going to be 0, 0, 1, 0, midterm 2. The next one is A prime, B prime, C, D, which is going to get us 0, 0, 1, 1, which is midterm 3. Next up we have A prime, B prime, C prime, D, which is going to give us 0, 0, 0, 1. Now, we already have that one, right? We already have 1, so we don't need to add it again. 1 is still covered. This is what I meant by don't try to eliminate the redundant terms at this step like the textbook tells you to. Just wait, because it's way easier to get rid of them after the fact. Okay, next up, A prime, B prime, C, D is going to give us 0, 0, 1, 1, or 3, which we already have. Next one, A prime, B, C prime, D is going to give us 0, 1, 0, 1, which is 5. Then A prime, B, C, D is going to be 0, 1, 1, 1, which is 7. A prime, B, C, D prime is going to be 1, 0, 1, 0, which is 10. And A, B, C, D prime is going to be 1, 1, 1, 0, which is 14. And there we go, that's our final answer. There is the midterm expansion, the generalized midterm expansion of our function f. To recap that process, you start with the function, you figure out what your missing variables are, you AND them back into the expression by using the variable or its inverse. You distribute that monster out to get this long, long sum of products expression. Then you label all of them and you figure out what you got. Any questions about that? What you got?
Why after the second one on that A prime, B prime, C prime, D, you skip to 3 and then 5 and then 7?
Say that one more time. The second one.
Like the
this one?
Yeah. Why
Okay.
do you skip after that? Why do you skip to 3 and then 5 and then 7 and 10, 14?
So you're asking why did I write 1 again?
Yeah, or why did I'm just confused with why it goes to 3 after the 1.
So we're not counting. That's the important thing.
Uh-huh.
We're labeling based on the variables, and all that was just the result of this distribution, right?
Uh-huh.
So there's no like relationship between one and the other. We're not counting anywhere. It was purely by coincidence that this one went 0, 1, 2, 3, right? So don't get hung up on that. We did this one. This was 1. We already had one. We threw it out. We should do the next one. A prime, B prime, C, D gets us 0, 0, 1, 1. That's 3. We already had that. So there's duplicate terms that can show up again and again.
Okay.
And like I said, the fact that it counted 0, 1, 2, 3 was like purely coincidence.
So you're not counting, you're just labeling the ones and
Correct, yeah.
on the prime.
Yeah, you're looking at what the variables are, what the literals are. A prime is 0, B prime is 0, and so on. And then you're saying, all right, that's 0, like 0, 0, 0 is binary 0, 0, 0, 1, 1 is binary 3, and so on.
Okay.
Cool. Good questions. Any other questions? All right. Cool. Let's move on. Oh, by the way, while we're here, just for fun, what is our function, the same function, as a product of max terms? We don't need to do any work to figure it out, right? We just look at our midterms and say what's missing. So 0, 1, 2, 3, 4, 6, 8, 9, 11, 12, 13, and 15, right? Those would be the places in the truth table where f is equal to 0. Which begs one last question before we move on. We take the time to write out f of a, b, c, d when we're doing this work. Is that important? I mean, yeah, otherwise we wouldn't take the time to do it, but why is it important? If I had just done this, f is equal to a prime, b prime, or a prime, d, or a, c, d prime, would it be possible to solve this problem? No, and why not? Because you don't know how many variables, yeah. So you have to define what the sort of variable space is in order to know what variables are missing, right? Now there's another way you could sort of cheat it, right? By saying like, well, we've got A, B, A, C, D, but that wouldn't really work, right? Just because a term is missing here doesn't mean it wasn't a part of the original function. All right. Can I erase all of this? So in keeping with that, there's one, the next topic is, well, here we started with a simplified function, right? Where some terms were missing. We had to figure out what the terms were. The next question is, well, what if terms are missing by design? So let me pose to you a sort of thought experiment. The title of this part is called Incompletely Specified Functions. Is it possible for me to... The fact that the board is like, or this thing is like covering like this, it's just bugging me.
It has a string.
Yeah, but I'm not gonna be that guy who like accidentally like shoots it up to the top.
I don't, but this room is old enough, I don't think that's on.
Yeah, see, look what you've done already. So it's just fine, I'm gonna make it lower. Yeah, okay. Great idea. It's on a string.
Really. You can mess with at this point.
Alright, here we go. Here we go. This all the way. These work. Yeah!
Oh, perfectly too.
Got it. Now if we do this, incompletely specified functions. Okay. Suppose that you are part of an engineering team. It's not like, outside this, realm of possibility for you someday. That's the idea, right? And you guys you're on a team, you're working on a system that has two separate logic modules, right? We'll call one in1, and we'll call the other one in2. And let's say that you are responsible for in2, right? Your buddy is responsible for in1. In1 takes 4 inputs. We'll call them W, X, Y, Z. And it produces 3 outputs that you take as inputs to your system. We'll call them A, B, and C. And your system produces the final output, F. All right, so we don't care what's going on here. That's the other guy's problem. We're responsible for this. And so when we're laying out the truth table for this, we put it up, we say we've got A, B, C, 0, 0, 0, 0, 1, 0, 0, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, right? And we've got our output F. Now here's the thing, when you sit down to do this design, the guy that's working on this says that terms 1 and term 6 will never happen. That there is no possible combination of inputs W, X, Y, and Z going into N1 that will give you a 0, 0, 1 or a 1, 1, 0. Right? They will never happen. They're not an input to your system. So what you do is you say, all right, cool. We X and F. Now if they do happen, that's on him, right? That's not our problem. So we X those out and we label the rest of our outputs. 1, 0, 1, 0, 0, 1. Okay. And like I said, these guys in 1 will never produce these inputs. But we have definitions for everything else. Now the game here is, first off, the truth table that we've got here is what we call incompletely specified. And the unspecified minterms are called creatively don't cares. What are they? We don't care. Our third and final bullet point here is, now we still have to design our system, right? So So we still have to choose. We can still choose we must still choose a value for each don't care. But we have some flexibility. We may choose either 0 or 1, depending on which gives us the best solution. Gives the most optimal solution. All right, that was a lot of writing. So yeah, the truth table that has don't cares is inclusively specified. Those midterms are called don't cares because we don't care what they are. We have to choose a value, but we can choose either a 0 or a 1, depending on which is more advantageous to us and gives us the most optimal solution. So let's take a look at a few cases. Well, this first one is 1. And let's say I assign 0 to both. So we're going to say, all right, both of them are zeros. So then f is a function of a, b, and c is equal to the sum of midterms. Oops, actually, I don't do that just yet. So 1, excuse me, 0, these are 0, so we don't care. 0, 3, and 7. So that's going to be a prime, b prime, c prime, or a prime, b, c, or a, b, c. And now we need to simplify it using the algebraic techniques that we've got. And hopefully we notice that we've got A and A prime both ended with B and C. That gives us uniting theorem. So that's going to leave us with A prime, B prime, C prime, or B and C, which has 2 terms, and 1, 2, 3, 4, 5 others. Any questions about that? All right, can I start drawing right here? So you can see this. So we assigned 0 to both of our don't cares, did the algebra, and that was the optimal result that we got. Let's call this one case 2. Says let's assign a 1 to the first one, A prime, B prime, C, and a 0 to the second one, A, B, C prime. Now our function, still a function of A, B, and C, it's going to be the same one, but now it's going to include A prime, B prime, and C. We're going to put a 1 here and say that we've got A prime, B prime, C prime, or A prime, B prime, C, or A prime, B, C, or A, B, C. Now here this one's nice, right? Because this first 2 terms combine across the C and have A prime and B prime, A prime and B prime. And the second one here is the same as we had on the other one. So A is combined. That'll leave us with BC. So this one is going to be what? A prime and B prime, or B and C, which has two terms and only four literals. So this one is an improvement over case one. All right, case three, assign 1 to both. So that means we're going to have F, A, B, and C is equal to, what do we got? A prime, B prime, C prime, or A prime, B prime, C, or A prime, BC, or another new one, A, B, C prime, or ABC. Let's see what that does for us. We can definitely do the ones that we've done before, right? So we can do, where are you at? A and D prime, so here's BC. We can do those C primes to get the A prime and B prime. Is there anything else we can do? Now we have these last two terms, C prime, so A, B, C prime, or ABC is going to combine over the C's. And that's going to leave us with A prime, B prime, or AB, or BC, which has 3 terms and 6 literals. And we won't do the fourth one, just because I don't want to. So of these 3, which is the best? Second one, why? Because it's the smallest, right? Yeah. So that's what I mean. You have to pick a value of 0, 1 for your don't cares, but you can pick whatever you want to see what gives you the best result. Now, we could take this a step further. Does anyone notice a way we could optimize case number 3?
Factor B.
Doesn't involve any factoring. What is that? A prime and B prime, or A and B? Talk about it last Wednesday. Wes? Guess we got a couple drinks since then. All right. Remember, so A prime, B prime, or AB, that's our equivalence operation, right? Look at the 2 bits to see if they're the same. It's also the XNOR operation. So we can combine this and be X or B not, or B and C. Which involves X or, but this is slightly more options. All right. But the punchline here is put 0s and 1s for your don't cares, see which one gives you the best sort of standard form solution, and move on with your life. Cool? All right. One last thing about don't cares, I'll write it down over here. Don't cares can be represented in either the minterm or the max term, the expansion. So for this expression, f, we can say that f is a function of a, b, and c is equal to the sum of minterms, 0, 3, and 7, or the sum of, they're all lowercase d, sum of don't cares 1 and 6. And we could also say that it's equal to product of max terms 1, 2, 4. Wait, hold on. That's not 2, 4, and 5. I'm just so used to looking over at the midterms and whatever's missing. And the product of don't cares 1 and 6. So not only can you use the don't cares in your midterm expansions, but you can also use them in your max term expansions. They are free for you to do whatever you want, depending on what gives you the right solution, gives you the most optimal solution. Cool? Any questions about that? All right. Give me like 10 minutes to erase all this. Are we good on that? Can I erase it?
Why was he able to reduce ABC prime and or ABC to AB after ABC had already been used to get BC?
Because we didn't eliminate ABC. It's not the same as the consensus theorem. So the question was, essentially, how could we use this to make multiple eliminations? And the answer is because in consensus theorem, right, if you eliminated something, you could use it again. But for uniting theorem, you can unite a thing with multiple terms. And a longer way to look at it, let me erase like this top half, and I can illustrate it real quick. Because it actually has to do with the first thing that we talked about today, which is, okay, let's see, we did the terms in question are these guys, right? A prime, B, C, or A, B, C, or that's A, B, C prime, or A, B, C. And I'm saying I want to use A, B, C to eliminate both of these guys. Now the way I can get away with it is because what is X or X? It's not 1. It's X, right? Anything or itself is equal to itself again, right? Which means that I could do this. I could say or, and just throw in another ABC, right? And now I can combine these. I could say, let's put them in parentheses to make it more obvious. A prime, or B and C, or and BC, or ABC, or my next one, A, B, C prime, or ABC. Now I'm free to use uniting theorem on both of these guys independently, right? Those guys into the A, those guys united into the C, and now I've got BC or AB. So that's what I'm doing in practice, right? In effect, I'm ORing another term so that I can use it more than once. And it happens so often that I kind of skip over it as a detail, and you can just remember that you can unite with multiple terms. And if you're not sure, like I said, this is what's happening under the hood. This is what backs it up. Cool? All right. Good, I'm glad. All right. Let's see, now there is something. So before we call it a day, I want to work out one design example. This will kind of set up Wednesday's discussion nicely, I think. But also it's kind of fun to say, well, now we know enough to actually make something that means something. So what is the most basic thing that a computer does? I got like 100 computer science, computer engineering majors. No one can answer the question, what does a computer do?
Adds things together.
What's that?
Does math.
It does math, right? At the end of the day, all a computer does is it does math over and over again. After everything, the RAM, the ROM, all the extra peripherals on the CPU, even down in the CPU, at the end of the day, there's a thing called the arithmetic logic unit, which is just the thing that does the math. And the most basic thing to do math with is addition. Which only has one O, because it's Monday. All right, addition. We spent some time talking about binary addition. We talked about binary subtraction. Now we actually want to design a thing. Here's like, computer architecture, 0.0.00001, right? Let's design a circuit. So design a logic circuit. To add two 1-bit binary numbers. Get any more basic than that. But we now know enough to be able to do this. Design a logic circuit to add two 1-bit binary numbers. Not even 2-bit binary numbers, not even 64-bit binary numbers. Just 1-bit binary numbers. But now we're ready to do it. So what we've got is, if A is 1 bit, and we're adding it to another bit, first off, how many bits is my result? And yes, it is kind of a trick question. One bit plus 1 bit gives me how many bits?
2 bits.
2 bits. Good. Right? Because, well, 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 0 is 1. But we got to account for that 1 plus 1, right? Which could be 1, 0. So we have this second bit. Yeah. So what we're going to do is we're going to say A plus B is equal to, let me write it a little lower because I'm running out of space. Let's say A plus B, and now when I write plus, I do actually mean plus. A plus B.
Plus
I
4.
know I sort of like been picking on you guys about that. Is going to yield a number that is, what I'm going to write is C comma S. Just to sort of differentiate the two. Okay? So the S stands for sum. We're going to consider that the actual result of our addition. In 1 bit, it seems kind of weird, right? Remember we said before that once we agree on the number of bits, we can't go over that many bits. So if we have 4 bits plus 4 bits, our sum can still only be 4 bits, right? Otherwise you have an overflow. And so that 5th bit is going to go into a special place. When you get to your computer architecture classes, you will learn that there actually is like a whole separate register to sort of hold the misfit bits, right? Like the carries, and there's some other ones that come along, but there's a whole register to hold these guys, but this is the carry. So A plus B gives us a carry and a sum. So now we just go ahead and make a truth table for this. We kind of already did it over here, but if we have A and B, all right, it's going to be 0, 0, 0, 1, 1, 0, and 1, 1. And on the output side, I'll have C and S. Now we already did it. 0 plus 0 is going to give us 0, 0. 0 plus 1 is going to give us 0, 1. 1, 0. 1 plus 0, excuse me, is going to give us 0, 1 again. And 1 plus 1 is going to give us 1, and 0. All right. So once we have our truth table, every output gets to have its own Boolean function, right? You basically treat every single output, even if you have multiple outputs to your system, you treat each one as its own individual circuit. It does its own thing. And so, all right, cool, super. Let's look at S. So we say that S is a function of A, B, and it's equal to the sum of midterms, what, 1 and 2. Which is going to be A prime and B, or A and B prime. Can we simplify it using our regular Boolean algebra? No, we can't, right? It's already sort of fully simplified. Now we can simplify it more by being fancy. What is this operation? A prime and B, or A and B prime.
XOR?
It's XOR, absolutely, yeah. So this is equal to A exclusive OR B. And that's our summing circuit. Now we need a circuit for the carry, so we'll say C is a function of A and B, and is equal to, again, the sum of midterms. This time it's just 3. That's equal to A and B. Can we simplify that any further? No, it's just one logic gate. So there's our two expressions, one for the sum and one for the carry out. Now the last thing to do is just go ahead and draw it. So we have an input A, we have an input B, the sum is going to be on the XOR gate, A and B gets us the sum, and then the carry comes off the AND gate, as B and A, and that comes out and gets us the carry. And there we go. This is what's referred to as a half adder. And we'll talk about why it's called half adder on Wednesday. So there we go. Any questions, comments, concerns about that? Again, like I said last time, right, the process is going to be exactly the same. We had something that we wanted to do. We derived a truth table that sort of explained all of that. Created our expressions, optimized them what little we could, and then designed our logic circuits. All right, that is it for today. Are there any other questions, comments, concerns?
Half
Yeah.
adder, right?
Hold on.
Half adder?
A half adder, yeah.
Half adder?
Yeah. Like I said, we'll talk about why it's called a half adder on Wednesday. Any other questions?
No, sir.
All right, like I said, don't forget that Unit 3 assignment is moved to Wednesday. But go ahead and do it tonight anyway, right? Save yourself the trouble. My office hours are from 3 to 5 on the Discord. If you don't see me logged in, you might just like hop into like my little office hours channel anyway, because sometimes I'm like doing stuff and I'll see it going on. Yeah, all right, cool. I'll see you guys on Wednesday. And like I said, the exam is probably going to be next Friday. Not this Friday, but next Friday.
And so, like, that's why I like memorizing a lot of the theorems and stuff, like finding information, all that.
I mean, you should, as like a intellectual exercise, as like a scholarly review.
I see.
But in the exam is taking them just like the
Oh,
assignments.
like-
The only real difference between the exams and the self-study assignments is I'm only going to give you like 3 days to do the exam instead of like 3 weeks for the self-study assignments. Yeah.
Gotcha.
Yeah. So yeah, so like you should memorize. It's good to memorize.
It's fun.
Because it's fun, right? Yeah.
I'm doing it.
Yeah. If it's not fun, what's the point, right?
Exactly.
I'm probably gonna put out the test, next Friday. That's like the 25th.